40 more seconds. You can keep talking a little bit. Yes, good afternoon, everybody. My name is Ryan Weber. I'm a research coordinator at the Climate and Environment Department at the Norwegian Research Center, NORCE. And together with my colleagues Rune Storvold and Eric Malnes from the Energy and Technology divisions, we're really happy to welcome you to this science session looking towards a digital twin of the Earth. Or, that was a digital twin of the Arctic. But we'll get to the digital twin of the Earth part, I'm sure. In some ways, I wanted to have a question mark at the end of our title because I think that there's the need for some questions about what it is we're actually talking about here. So from my perspective, in my previous professional life, I worked a lot with green building. And 15 years ago or so, the hot topic or the hot discussion in green building was BIM, Building Integrated Management. And this was a tool that essentially created a digital twin of a building to make the resource flows and the understanding of the systems of a building digitalized for the effective management of energy and resources in buildings. And the notion or concept of a digital twin largely comes from the industrial sector, from these industrial processes and systems in rather closed environments that are in some ways easy to digitize or easy to envision or model in a system. And when we start talking about a digital twin of the Arctic or even a digital twin of the Earth, I think that there's a lot to be discussed in terms of what we're talking about. I think we can understand that we can develop digital twins of different components of a system, say of the biological or chemical or even socioeconomic components of a system. But I think the question also has to be about how do these different components work together in a systems perspective. So I think that that's one of the things that I would like to introduce and say as kind of key questions that we want to, or a key question that we want to look into through all of the presentations today. But we also have some other key questions that I wanted to address and hope we can address in this session. In addition to what does a digital twin of the Arctic really mean? What should our ambitions be? What are the potential effects of a digital twin of the Arctic and the increased use of AI in this digital twin concept for the Arctic? What are the options or solutions from a planning perspective, from a policy perspective, from a perspective of the local communities that are living in the Arctic? And can we think of what the possible impacts can be for these local communities, both positive impacts, but also potential negative impacts or negative challenges? So through some pointed scientific topics and discussions and presentations that we're going to have today, I hope that we can also carry forward and you can join us for the panel session that will be hosted by my colleague Rune Storvold to scope out a little bit from the individual presentations and again talk about the concept of a digital twin in the Arctic in a more broader or foundational perspective. So I'm really excited. We have a lot of exciting presentations to hear from today from exciting researchers and scientists. So better them talk than me. So I would like to welcome our first presenter, George Gartner, who has a presentation titled What We See and What We Don't See, The Relevance of Maps in a Sensitive Region. George? Some water if you need it.
Yeah, thank you very much for the introduction. My name is Georg Gartner. I'm from Vienna, Austria. No Arctic region there, but the Alps. And that's why we are, of course, interested in that. I think it's a fantastic conference, and I'm really happy to be able to be here. I'm currently president of the International Cartographic Association, and my message I would like to get across is We are talking about a sensitive region, the Arctic, and I think we would agree that everything happens somewhere. What do we do if we collect something about what happens somewhere? Is that we make models, as you have said, and what we produce is we produce data. That's what we do. And as a cartographer, I would say, well, fair enough, it's all there. Here it is, the information I would like to get across to the Prime Minister, which has been here this morning. Here you can see the validation of the global warming in the Arctic area, but I don't get the message. So what's the point? The point I want to make is that we have a high responsibility to aware blurred images of the world. We have to avoid that what we communicate about our results, about our insights, can be consumed properly by the public, by decision makers, by the indigenous people, by whomsoever. Can we make sure to make that work? And my argument is we need this. That's what we need. It becomes immediately clear that holistically speaking, I get a picture of something. I can work with this, so to say. What do I do? What are the benefits which we need? We need to cross-check that, how we communicate, how we present our insights with what our communication channels are actually offering. And I'm arguing what we need to gain is something like this. I would like to make sure that people are understanding something spatially. Something is happening somewhere. What does that mean? There are relations, spatial relations. How do I explain spatial relations? Something is close to something or related to something. If I'm using words, complicated. Put it in a map, easy. Everyone understands that. Evoke associations. Maybe allow spatial planning. How would you do that differently than to allow planning in your brain, so to say, by underpinning it with something like this? To be aware of the space, of that environment we are talking about. To analyze it, to understand the context we are in, maybe look back into the record, into the history, and then by this understanding the processes which are ongoing, as well as allow spatial learning, and simply have effective communication, and eventually also an emotional response. One of our students have once at the Arctic Forum presented a cartographic expression, maybe you've seen that, making a plate with a map of the Arctic. And during the conference, at the beginning, she put ice cubes into that plate. And during the conference, those ice cubes melted. That was a strong, emotional, associative way of communicating something. That is something which we want like to do. And I'm arguing that is because of the pure nature of maps. Maps tell us something about relations, spatially, spatial relations. That's what they do. That's a benefit. Maps evoke associations. If I tell you, this circle tells me that two cars have crashed into each other, and I ask you, what is your association? I ask thousands of people, that's what we did. I get a number. You don't know, you have to associate. I get a number. You say 45 kilometers per hour. I do this. I ask the same question. What do I get? A different number. We evoke associations with how we communicate something. We are not neutral. We are not objective at all. That's the power of what we have to consider as well. We put something into context. We put something into relations. We have the possibility to become aware of what we are talking about, to make it really speakable, so to say, understandable in a sense. To allow for an analysis. Maps are crucial in that respect, that I'm understanding that relations from an analytical point of view as well. And it's important to see that whatever we communicate something, but at the same time we also leave something out. It's always a selection, it's always an aggregation, it's always a statement. We are never ever objective or neutral in a sense, and that's important to know, and maps are tools for this. They allow us to have a historical context to go for a process and then understand what's ongoing in this respect. And also, we are determined by what we see. There is nothing wrong with making a map south-oriented, but it's confusing, it's irritating to all of us. Correct? But I mean, here we are, the Earth is a three-dimensional body. It's just that because we do it north up. We don't need to. We could do it this way. It's just that the map we see every day determines our understanding of the world. Very powerful, important to know. And I think a map like this, which shows the Grand Army of Napoleon walking to Moscow and back, and what happened all the time, if you have to tell that in different means, with different meanings, with words and so on, you will need to write a book about that. It's all there in one map, so to say, what allows that. And I would argue maps have the potential to please. None of us will ever be able to see that the seabed floor without the water there, but we can allow that to show that. And that's all done by this big industry. I call that the geospatial ecosystem, that the digital twins, the AI, the machine learning part of all of this. Cartography is heavily affected by that, by automatization, automatic map production, as you probably know. Of course, maps are services in the meantime. We have a big industry, but I'm always saying what we do with this is we are producing data, first of all, but then it's important to decide on what do we do with it, so to say. So those services which we all consume, if we're using maps on our mobile phones, on our computers, do they still fulfill the needs and demands of those questions which I've presented at the beginning? That's the question. And I argue that will be ongoing because there's a big ecosystem behind that we're building those services, combine it with social media, with digital twins, as we've heard about that, and it's getting closer and closer, and it's not a vision anymore that we have contact lenses where you can put a map on top of it, so to say, augmented reality getting closer to our brains, so to say, in a sense. That's also something which is ongoing. And then also building that into a linked system, into a semantic web system where everything becomes related in a sense. Now, is the model really the reality? That was the question of our chair, and I, as a cartographer, would say no, it can't be, never, ever, so to say. So it's important to understand that as well. But building those knowledge infrastructures is part of the game, in a sense, in this respect. And in respect to AI, cartography is heavily infected, but what do we do? If I give you a map tomorrow, do you trust that map? If you don't know who has produced that map? That's the big question. The question is not a technical question. We will produce maps by AI. We are able to do so. Can you trust it? That's the question. The main question to our societies and our technologies is the trust question. Our answer to that is we need to have two answers. Go deep and go wide. If you tell me something and I don't trust what you say, I ask you. I want to find out about your rationals, your arguments. I want to see transparency. I go deep. If I still don't trust you, I ask your neighbor. I go wide. That's what we do. We ask somebody else. And exactly the same thing we can do with maps and geodata. Make everything transparent. Every single decision which has been done to make that map look like this, that model look like this, make it transparent. And if you can't do it, at least describe it in a sense, because it's sometimes hard to do it. And the other thing is, because of semantic web and linked data, make it wide. I give you a map of the Arctic. I have metadata. Every map has metadata. Give me an alternative representation with a similar metadata set. And I make up my own mind. So that is the way we are thinking about that. And as I said, I'm currently president of the International Cartographic Association. We're working with the United Nations quite a bit. We've published a book on mapping the SDGs, which is openly available to all of you. And if some of you are interested to join us in one of our upcoming conferences, I would be happy to see you. Thank you.
One quick question, if anybody has a question. I was certainly intrigued by your presentation. One of the maps you showed was from my previous workplace, that we worked hard to produce maps for the Nordic region.
Excellent.
One thing I want to ask, though, is I think you brought this up in your last couple of slides, is about the issue of trust and who has made that map, because the cartographer themselves has quite a lot of power in presenting data or presenting information in the way that they like. And so I'm wondering if you can explain a little bit more about what opportunities, maybe in terms of innovation, in terms of AI, can give to the user of the information in terms of viewing and getting into the details of data?
Well, I'm not sure if that is a task for AI, to be honest. I think it's a task of making, I call it an ontology, if you know that word. So describing the processes basically behind that. So I was comparing that with, in my brain, what I see now, what I experience at that conference, I have a lot of information in my brain, but if I have to explain that to my wife when I'm coming back home, I'm doing an abstraction. I'm putting words on top of my experiences. I'm making an abstract sentence. And that is a black box in a sense, a little bit, the selection and aggregation process. And the same is true with other communication means in a sense. But we need to make sure that those processes are at least described in a sense. And that is something which we need to describe on a structural level, schematic level. And AI is rather used for doing those processes, but not in a, let's put it this way, there is this explainable AI, which you might have heard about. So that part is still very tricky in cartography. Let's make that message across. Yeah.
Thank you very, very much.
Okay.
It gets us to the point that a big component of digital twins is the visualization and the dissemination of information, and mapping and other illustration and visualization is a core of that. Thank you very much.
Thank you.
Next, I would please, and this goes for everybody, forgive me if I mispronounce your name. There's some tougher ones. So next, I would like to welcome Ilaria close, Crotti, to give a presentation on improving air quality forecast in the Arctic with machine learning.
Thank you. So I'm afraid to say that my presentation will be more technical. So I'm very happy to be here. My name is Ilaria Crotti, and I'm a researcher at the Joint Research Center of the European Commission in Italy. And I'm happy to be here because I'm a part of the Arctic Passion Project, which is an Horizon 2020 project, which is implementing the Pan-Arctic observing system, or trying to overcome the actual flows. And I'm part of one of the teams that is developing one of the services that will be available for communities in the Arctic. My service and our service is focusing on improving air quality forecasts using machine learning. Okay, so our service is tailored for PM10, so for atmospheric pollutant, which stands for particulate matter, which are very fine particles with a diameter below 10 micrometers, and they are very dangerous for our health because they could be inhaled and create problems at cardiovascular level, at respiratory level. So we really need to take care of this and to really monitor the concentrations in the atmosphere, also because the World Health Organization in 2021 revised their guidelines and provide more stringent guidelines for concentration, especially for mean annual concentration. Nowadays, the best one is considered to be 15 microgram per cubic meter, and the mean daily concentration is 45 microgram per cubic meter, and we can see from the map here of Northern Europe. Not most of the monitoring stations in 2022 meet these requirements. And this is due to the fact that there are many economic activities happening in Northern Europe, such as shipping, as we heard before. We have mining and many others, and settlements, so housing, heating, that could cause the increase of PM10 in the atmosphere. So nowadays, the forecast for PM10 is provided by the Copernicus Atmospheric Monitoring Service, which gathers 11 models developed by different countries in Europe and use ACMWF data for meteorological variables and also for emission sources, and they provide a daily forecast for PM10. But if we look at the error associated to this forecast in comparison to the observations of the field observations for North Europe, we have kind of a high error, and one of the issues is that concentration here are lower in comparison to the other parts of Europe, and also we don't have, not many stations are used to in the data assimilation process of CAMS. So for this reason, we want to see if we could help this forecast using machine learning. So we published a study last year where we used 6 monitoring stations in the Arctic that provided data for 3 years between January 2020 and December 2022 without only small gaps in the data, and we combined the observation with the 9 CAMS forecast models that I said you about, and we put all the data together, testing for different machine learning architectures. We used eco-state networks, long short-term memory, gated recurrent units, and recurrent neural networks to provide a 24-hour forecast. Our data were encouraging because if we look at the errors provided by this forecast, we have here, so we have here on the left, so we have here the 6 stations, and on the left side we have the error, the mean square error for all the CAMS models, the orange bars. And then on the right side we have the error for our neural network forecast. And as you can see, the error reduced for all the stations, and the error is between the forecast and the observation, so how much we are close to the real data. And above all, we have mean square error improvement of 20 and 40% for all our tested algorithms, and among all, the long short-term memory, which is the dotted green, is the one that better mimic and the observations, which are the blue line. So this is the kind of architecture that works better for our forecast. So since this preliminary study provided good results, we want to improve it and to extend it to 100 stations in the Arctic, in Northern Europe, because we don't have many stations, unfortunately, in the Arctic, but we could use the data. And so you see the dot here. And the idea is to use more data and more PM10 stations, and to include meteorological variables from the ACMWF, such as temperature, planetary boundary layer, winds, precipitation, humidity, and so on, as input data to our model. And we want to go a step further using different architecture, which are transformers that tackle better long-term dependencies and also are very flexible because they don't need continuous data. So if there are some gaps in the data due to problems in the stations, they would work anyway to provide a forecast. Yeah, and this will be our service that we want to develop for communities in North Europe. So it will be a very simple map where users will be able to click on a station to see the real-time data for PM10 and our forecast. And then they will also be able to download historical data, to download this is just a demo, but to download also the forecast that we are providing, and then we'll provide also a nice overview with nice colors to see where the pollution is higher or lower. And we are thinking also to provide a simple daily bulletin where the users can see where the forecast is giving higher concentration in certain area. And that's it. So thank you for listening. And I'm not the machine learning person here. So if you have any question, please ask. But if there will be very, very technical questions, Alice is my colleague who's working with that, and I will forward her the question. Thank you.
Any questions?
I'm worried it's a little technical. So, but you showed a series of different architectures that you were leveraging, and I was wondering if you had advice for the room on how many architectures should you test? How do you pick which ones work? Do you really have to train 6 different models? Were you involved in? I'm sorry if it's too technical.
No. I didn't train the model, but since I'm a part of a team, I saw the process. So I could say, first of all, you have to decide. I think it's all based on the data that you're using. So at first, we tried neural networks, and because we choose data that didn't have long gaps. So we were like, okay, we'll choose the best data set that we could have and we try to make it work. So we try to work with neural networks because they seem to work in a good way according to our review, paper review, on time series and with only small gaps. Now we said, okay, we tested this, now we are moving to transformers. We obviously won't test like 100 models, we stick to 4 or 5. And also it's very time consuming, and we don't have much time because our project is ending next year, so we have to find a solution. But yeah, and now we say, okay, if we want to extend to 100 stations, maybe we don't have such continuous data, so we are trying something that will work even if we don't have continuous data.
Is the objective to extend it to 100 stations in the context of the Arctic Passion project? Okay,
yes.
So it's within the lifetime
1 year,
of... Okay,
so
more information about this can certainly be found at the Arctic Passion website?
On the Arctic Passion website, and when our website will be ready, it will be accessible from there. It's free, and only you need to register with an EU account, but everyone can get one for free. So please visit our website.
Thank you very much. All right, next up we have Are Frode Kvanum, developing a deep learning forecasting system for short-term and high-resolution prediction of sea ice concentration. So welcome.
Thank you, Ryan. Good afternoon, everyone. My name is Are Frode Kvanum, and I'm a PhD student at the Norwegian Meteorological Institute. And on behalf of my colleagues, I want to present to you today how we developed a deep learning-based forecasting system which is able to predict sea ice concentration on both short-term as well as high resolution. I want to start off by briefly describing the problem. As we all know, as participants at Arctic Frontiers, the Arctic is rapidly changing, and it has severe consequences for the Arctic. For one of the variables, which is sea ice, we do see a steady decrease both in extent, but also a thinning. And as a consequence of that, maritime operators see opportunities to increase their presence in the Arctic, especially during summer, but also in the shoulders extending their period. And this is true for several different industries, such as shipping, fishery, as well as tourism. We have also seen recently in the literature that deep learning-based systems are able to forecast sea ice on a seasonal level, on seasonal timescales. But for this work, we wanted to see if we can use high-resolution sea ice data to train a neural network to predict high-resolution sea ice for short lead times, 1 to 3 days ahead. In order to construct the dataset, we considered different physical as well as temporal technicalities of the different data available. We use data which covers the past, the present, as well as the future. For the current information, we use sea ice charts, which are developed locally here in Tromsø by ice analysts at the Ice Service of Met Norway. And they are on a 1 kilometer resolution, and you can see the domain which they cover here. We also use past satellite observations to create a sea ice trend, which covers the past. And then we also include the future by including atmospheric variables from an Arctic regional weather forecasting system. And from this system, we extract both the winds as well as temperature to see if the correlation in the atmosphere of the future can help drive the network forward in sea ice concentration prediction. And then finally, we also include a land-sea mask. And I can say that this figure kind of covers what we trained on, but we trained on 2019 and 2020, so it's a limited set of years, and then we verified the network for 2022. For the deep learning implementation, we utilized a variation or a modification of the traditional UNet architecture, which is a very common architecture for image-based deep learning. Training this network takes approximately 3 hours, but you do it once. Once the network has been trained, we're able to produce forecasts in approximately 6 seconds on a CPU, and we can also scale this architecture to consumer hardware. This is what it looks like when we predict using this deep learning model. On this figure to the left here, we have a CIs chart for the 23rd of March, 2022. And in the middle, we see a CIs chart for the 25th of March. To the right, we have a 2-day targeting deep learning system initialized on the 23rd, meaning that the CIs chart here is used as input. And then, of course, it targets the 25th, meaning that it wants to recreate this situation here. And immediately, one striking difference from the deep learning predictions compared to the ICE charts are the lack of details in the different CIs contours or the CIs edges. And we can also see that this gets increasingly so for increasing lead time. So for longer lead times, the predictions are smoother. However, from the physical perspective, it is able to recreate some of the phenomena we have seen in the development here between the 23rd and 25th. For example, this open ocean area is being closed successfully by the deep learning system. And this advection of CIs here has also been somewhat resolved, meaning that it is able to replicate some of the physical processes. In order to verify the system, we listen to what end users request in terms of trusting forecasts, CIs forecasts that is, and end users report that they want the position of the ice edge. For us to do this, we combine the length of the ice edge with this integrated ice edge error, which is a spatial representation of false positives and false negatives, to get this ice edge displacement error. And the ice edge displacement error is a very intuitive metric, since it gives us the position of the ice edge in kilometers or in distance units. But we can also use this metric to compare forecasts across seasonalities, meaning that we have a metric which is independent of seasonality. So we compare our forecasts against several baseline metrics, as well as some physical forecasting systems. For the baselines, we utilize persistence of the ice charts, as well as a linear trend, which we have computed from past satellite observations. And for the physical forecasting systems, we use 2 different CIS models, NextSim, which is pan-Arctic, as well as a regional ocean and sea ice model, Barents 2.5, which covers the Barents domain. And this is the result from the forecast into comparison. The deep learning system is the blue line, and as we can see, when we consider different concentration contours or ice edges for both 1, 2, and 3-day lead time, the deep learning system successfully achieves the lowest error for all considered dates and concentration contours. We can also break this up into a seasonal distribution for a single year, in this case for a 2-day lead time. And now the deep learning system is the green box. And we can see from the box plots that the deep learning system for all seasons achieves the lowest mean and median error. It also has the lowest spread in error when compared to the different products, and this is true for all seasons, as well as for all concentration contours. So this tells us that the model has some degree of skill, and that it is not good at just one single season, it's good for all seasons, so it's representative. And beating persistence of the ice charts is very difficult for short-range forecasts, and this is something the system is able to do, which gives us more trust that it is a skillful prediction system. So finally, we wanted to see how good the model, how the model utilized its different predictors and which predictors were important. I want to focus on 3 things from this figure. We have for 1, 2, and 3-day lead time the importance of the variables in terms of if you remove a variable, you will achieve a worse score compared to the baseline reference all predictors are included. I want to focus on 3 things. First, here we can see that by using the current, or by removing the current CIs information, at increasing lead times, the difference in error decreases with lead time. While at the same time, we can also see that including or removing these atmospheric forecasts causes a higher difference from the reference at increasing lead times, meaning that for longer lead times, the system tends to use less of the current state of the sea ice and more so use the future state of the atmosphere to make good predictions. Finally, we can look at this past trend using this past information. And for all lead times, it seems to be relatively unimportant. And this might be because the variable is, or the predictor is maybe coded a bit bad and that the network isn't able to use it. Or it might tell us something that including past information is not something such a network, this UNet type of model, is able to utilize. So to summarize, we have seen that a lightweight deep learning system is able to predict sea ice concentration on short timescales and high resolution, and this is despite being trained on a limited amount of 2 years. We have also seen that the deep learning system is able to outperform forecasts, physical forecasting systems, as well as relevant baseline metrics. We have also seen that atmospheric forecasts, the future of the atmosphere, is important to create quality forecasts, especially so at longer lead times. And finally, this predictor importance analysis might suggest that a higher focus on explainable AI and explainability for these systems is necessary, both for us developers to make better model choices in the early runs, but also as a tool for end users to be able to interpret and use these forecasts and aid them in decision making. Thanks for your attention. I also want to say that this work has been submitted to the CRAS for discussion. If you want to read this, here's the DOI. It should be online very soon. And if you have any questions, feel free to ask me. Thank you.
Any questions? You make me ask all. Yes?
Nobody asks question, I will have to play the devil here. So when there's sea ice closing or advancing in some area, so and people ask you how confident you are in that forecast, what can you answer?
How confident I am in that? I would say maybe one of the drawbacks from this approach, and maybe that's a bit inherent to the data, is the lack of being able to create probabilistic forecasts. I could, of course, create it's a discussion in itself how to create uncertainties. You could run an ensemble of models, but since we're working with deep learning models, should you then perturb the predictors? Should you perturb how different models are created to create an ensemble of models? And that gives different difficulties in terms of interpreting this ensemble. An ensemble of different models aren't necessarily giving you could say, distributions you can compare, the comparative distributions. So, and also the ice charts uses categories for sea ice, and it's not a uniform categories. That also makes difficulties to interpret how a spread would be. So I would say that this work gives some indication of how to develop such a system, and it might be good if you verify it further, but at this stage, I would never be confident by giving this to some ship and say, this is how it's going to be. I wouldn't trust it like that, but I think it gives some interesting insights in how these systems can be developed, yes.
Thanks, I think it's quite impressive.
Thank you.
Now I'm going to go against my better judgment and ask you one more question, very open question, and ask for a fairly short answer, but where do you take this work from here? What are your immediate goals in terms of next steps in terms of this work?
I think there's two approaches. The first is to increase the validation period, see if it works, if it's still good for 2023, 24, etc. And then I think, as the last question also went into looking into probabilities and increasing the spread of the ensemble, to not have a deterministic forecast, but to have ensemble forecasts.
Thank you.
Thank you.
If we have time at the end, we can come back and take some additional questions. Also fun later. Great. Yes, next we have Elizabeth Itborg, how marine aquaculture sites can provide data for climate change assessments. So welcome.
Thank you. Thank you for the nice introduction, and thank you for the opportunity to present at the Arctic Frontiers. The presentation I will present is part of the work done by Nofima and the University of Stirling. And to put my title into context, what we try to do when we work with aquaculture and climate change is to look into how the different scenarios provided by the International Panel of Climate Change from the global perspective. They are downscaled to a national level by the Institute of Marine Research. And we are trying to look into these scenarios to see if we can project how local scale conditions will look like, so that we know what kind of changes that will happen in a specific farm, for example. And we are interested in looking at the climate change at specific farms to see how this will affect the fish health, production procedures, for example, and also how we can better design our research trials when we do tank experiments with fish, for example. But when we started this work, we found that there were some challenges with the national and the global models. As you can see, the resolution here is not really good. You can hardly see Lofoten area in the downscaled model projections. They are 10 by 10 kilometers in resolution. So when we look at aquaculture, we know that that's going on in our fjord systems. And the fjords, they have different temperatures depending on where they are. If location is in the outer part of the fjord or in the inner part of the fjord, they will have different temperatures, for example. So the resolution in the models would need some adjustments before we could use them in our studies. So first we found a procedure of how we could calibrate the climate models to suit the local conditions. And we did this by contacting farmers and getting a lot of data from them. And we used this data from the actual sites to calibrate the climate models. So you can see to the left here, the red lines is the uncorrected model output versus the farm data. And after correction, the model was fitting to the actual data from the farm. And this is possible to do because the climate models, they were started in 2015 or something. So there's an overlapping period that can be compared with historical data. So this has been published if you want to read more about it. Then we use these projections to look at the farm data, if we could actually predict the temperatures in a farm setting. So we found at this location in 2030, they might expect temperatures up till 20 degrees. And previously, they haven't experienced temperatures above 15 degrees. So they will have a 5 degrees increase in less than 10 years. And that's a huge increase if you're a cold water fish in the pens. So this information can be very relevant when it comes to, for example, climate adaptation strategies and so forth. But when we went to farmers to get this farm data, they always came back to us and said, but you can go to BarentsWatch, all the information is there, you don't need to contact us to get it. So we wanted to see if we could go bigger and do these projections for all farms in Norway based on data from BarentsWatch. And BarentsWatch is a portal that collects data from coastal activities. And they also have a site for aquaculture. It was launched in 2012, so there should be enough data collected there to work with. BarentsWatch, they have more than 1,000 sites from aquaculture. They measure temperature weekly. And as I said, they have time series back from 2012. So we wanted to see if this data could be used to, for example, calibrate the climate projections, like I just showed you. But when we looked into the data, we found some problems related to this. Because it turned out that the farmers, they don't have a specific day when they sample the data. It can be any day of the week. They don't have a specific time, so it can be any time of the day. And they are not really specific about the depth. So it can be between 3 and 10 meters, and that will depend on temperatures, for example. So it was very difficult to get some real sense out of it that could be used for the climate projections that we wanted. We had to do a lot of manual data cleaning before we could look into the data sets. And we saw that we needed a much higher level if we wanted to use this data. We compared it with the farm data, and you can see the red line here is the daily differences, and the blue one is the weekly temperature. So there's really a big change between the different timings. But there is a big potential out there for aquaculture sites to collect huge amount of data. If we compare the Barents Watch site with more than 1,000 sites, with the national stations run by IMR, the governmentally owned stations, that they have only 8. These sites from national stations, they collect, of course, a lot more data than the farms do, but the potential of using these sites, these aquaculture sites, for more data collection should be used better. If you just look at this small area down in the south, it's more than 60 different locations in a small fjord system. And imagine the amount of data you could have if you just collected it properly. This data collected could be used for historical evaluation, could be used for looking into changes that have occurred or are occurring at the site per se. And it can also be used for future projections to know that what kind of changes we can expect in these regions. For a 10-minute presentation, I don't think I need to sum up, but just want to say that Barents Watch, initiatives like Barents Watch, they are essential to provide open access data, but we need to make sure that the data can be used for something else. At the moment, it's not very useful for studies like we are looking into, but the potential is really there. We have submitted a paper on this to aquaculture, and hopefully it will be published there if you're interested in all the details. Thank you.
Questions? Is there any possible way of there being some regulated guidelines that fish producers shall follow in terms of the quality control of these monitoring activities? I mean, obviously the relationship and impacts between aquaculture and climate change, but also aquaculture and marine ecosystem health and biodiversity and eutrophication and fish health. So couldn't this be considered as something that could be regulated, that they have to have some quality control in terms of these measurements? Has there been any discussion around this?
It could be a question to the audience. Any politicians here, or
any politicians
No,
here working in the aquaculture sector?
It is being discussed, and I know that a lot of farmers are interested in providing more data to a platform like this. But as it needs some guidance, it needs some regulatory systems. It needs to be discussed, I think. So that's what we hope for when we publish this paper.
And maybe on a very general question, what happens with a warming North Atlantic and a warming coastal environment in terms of fish farm production? Does everything just migrate north?
Yeah, it's not a short question. When you saw that one of the farms in mid-Norway, it might increase with 6 degrees. I think that's a big leap. And it's not only the temperature that follows with climate change, it's all the secondary stressors and all the parasites and the infections and all of these things that we need to consider too. So it's not just to move everything north.
Understood. Thank you very much.
Thank you.
So we've had mapping, air quality, sea ice concentration, aquaculture, and now on to search and rescue. So I would like to welcome Sara Aparicio, giving a presentation on a multi-sensory search and rescue based approach for melt pond retrievals. Yeah, you can take that. You caught me off guard there.
Sorry. So my name is Sara Aparicio. I'm doing a PhD in the Nova University School of Technology in Lisbon. very far from here. And by the way, I'm sorry, I'm too used to acronyms. SAR here means Synthetic Aperture Radar. No, sorry. I'm so used to these acronyms that I should make this not an acronym. So I'm interested in looking at melt ponds. These pools that form in the Arctic in the sea ice of the Arctic that form during the melting season are one of the most important and variable factors affecting the albedo in the Arctic sea ice. And because of that, they are of a high relevance for the Arctic energy budget. Because as you can understand, they lower the albedo of the ice, there is more radiation, which leads to further ice melt, increases the size of melt ponds, and this is an ongoing positive cycle. They behave differently depending if they are on multi-year ice. They are smaller and darker and deeper. And on first-year ice, they are wider and shallow. And they tend to be wider and cover more space. And what happens here is that over the past 50 years, multi-year ice has been replaced by first-year ice, which means that melt ponds were of great importance, and they are becoming of growing importance given their relevance on the Arctic sea ice. However, despite their huge importance, they are poorly represented on sea ice models, and they are not explicitly included in most climate models and atmospheric reanalysis. So what is the big issue here? Is that they are actually, the lack of knowledge of melt ponds, the lack of parameterization on melt ponds, make them as pointed. They are pointed as one of the main causes of uncertainty on sea ice predictions and underestimations. So this is why I'm so interested in looking at them. So what is my role or my question or my quest here? And taking the words of George, I think the first presenter, to see the unseen and on maps and so on, I want to use radar image to see melt pond fractions, so fraction of ice ponded or covered by water. Because now we have melt pond products that are based on optical data, but in the Arctic, as you look at the sky, we are always covered by clouds, meaning that we cannot always rely on optical satellites. So I want to go for radar. So here is my first issue. I don't have this type of data now. So I want to create my training data set that will feed my deep learning model to make this. So my first methodology is to actually create my training data, which is the core of any AI pipeline. So I grabbed this optical data based on Sentinel-2. I grabbed several bands of Sentinel-2. I did some, just a random forest, 15 trees, and I was able to generate these maps where each pixel corresponds to a class, melt pond, water, or ice. I choose many locations. This is manual work, very, very boring, but very, very necessary. And so with the random forest, and I got pretty good accuracies, over 90%, but this is expected, no? Because they look so different. I got my binary map, and then I reduced the resolution to get the percentage of water over ice. And here, finally, I have my training data for my deep learning model. So the melt pond fraction will be my output, and my input will be SAR, synthetic aperture radar data. But I'm wondering, will my deep learning be that smart to look at SAR data and predict melt ponded area? Because I'm not sure if you're familiar with SAR data, but the dark areas there means a specular reflection. So the radar emits a radiation, and it works like a mirror. So we see black, there's nothing there. In white, it means that the roughness of ice emits more radiation back to the satellite. So let's see, and you see in other places you don't see this correlation between SAR and melt pond fraction. So I'm a bit worried, will this idea work out or not? These are the different data sets that I did. Besides different polarizations of the radar, I also included the angle of the Sentinel-1, and I also included wind, because if there is wind, the water surface become a bit rough. So the backscatter, perhaps the satellite backscatter will look more like ice because we will see more light. And also, I decided to make different crops of images. So it will work like a zoom out, if we think that way, because the bigger image, there's more special correlation among the pixels, which in principle will make my network smarter. I also did another, these are different training data sets that I created. In this one, I also removed the water to not be confused with meltbones. And in all of these are just different pipelines for the generation of the training data set. I basically changed the resolution of the meltbone fraction, and in this one I also added a binary map of meltbones. So, now the fun part, the deep learning. I was not sure which architecture to use, but one thing was for sure. I wanted to start with something, instead of starting with a Godzilla network, I wanted to start from scratch with something simple. And between a multi-layer perceptron and a CNN, I went immediately for a CNN because in a multi-layer perceptron, my image will be converted into a vector, and each pixel will represent one feature. But I want to look at the image as a whole, and I want to have the information of the neighboring pixels, which our convolutional layers allow us to take. So, and also, they are more efficient in what regards parameters. So this is my initial. I started with just 3 layers. Then I understood that I was getting better results adding batch normalization and Likert-Lelu. And the activation layers, as common practice that I use in all the layers, were Likert-Lelu, exactly. And my last layer, it's a linear layer, because this is a pixel-wise regression. I'm not doing classification. And I found very hard to find online people doing pixel-wise regression, so at some point I was wondering, is this even a good approach? And then I find someone complaining about this in a forum. They could not find anywhere online about this. So I'm looking for if anyone has comments on this. So this is my input. I also changed sometimes what I put as input. In here I have two polarizations and one angle. Sometimes I put wind, and I'm making all these tests. And it's my output. And the first results. I have to confess I picked the best images. Some do not show a great correlation, but this already is giving me a lot of hope, because this is just on 8,000 images. I'm already getting some similarity between, is there a pointer? Exactly. So here you see the actual meltbound fraction, the one that I originated initially, and this is the predicted output. I can see some similarity, so this is giving me some hope that perhaps if I feed with enough data, I can create a model smart enough to look at SAR and retrieve from their meltbound fractions. This is just other aspects, and these are my next training data to analyze. And finally, to conclude, what are the next steps to improve this? One, critical, essential, is to increase the amount of data. More data, the smarter the model gets. Also to perform augmentation, but being careful to not create fake SAR images. I will just make like little rotations or flipping, because I cannot change the physical world. I need to keep ensuring that data quality is there, because sometimes I have artifacts from the satellite that I don't want the model to pick up and be thought wrongly. And these are some examples on my first trials. These were some artifacts that I did wrong, but the model will predict them quite all right, so this gave me some hope in the very beginning. And finally, speaking of Godzilla's neural networks, in the next ones I want to try a SegNet, because I see it's very good for pixel-wise segmentation, so I'm having hopes it will be good for this pixel-wise regression. And thank you so much. I'm looking forward to questions and suggestions. I'm missing here my email, but we can catch up later. Thank you.
Any questions? Any suggestions?
Really fantastic work, and I think a CNN is totally perfect for what you're doing. I've done something similar, so we could talk later.
Yes,
But
please.
I was actually wondering about the SAR images, and sea ice can have a roughness associated with it. And so are you having any troubles with a rough surface versus a smooth surface, and multi-year ice being... Okay.
Where should I start? So, can I have the presentation again? Because I actually, in between my presentations. Thank you. I see them here, but it's okay. So, in fact, this is not here just for aesthetical purposes. I wanted to draw this attention. So, in regard to the roughness on different types of ice, I even have troubles on understanding what is a melt pond or not on optical image. So, oops, here, for instance, okay, this is clearly a melt pond. It is, yes, it is. Sometimes I have issues on interpret optical data if it is very, very thin ice that you can see the ocean below, or if it's water. Sometimes there is actually leads and open water. They are very dark, and sometimes there are melt ponds that, is it a melt pond or open water? So what I do here, and to make sure I ensure the best quality possible, is I just pick up what I'm totally sure. So in this image, for instance, I will go there. No, I can use this. I was ignoring this part to not pollute the quality of my training data. This is why the part of collecting this was so, I'm trying to find the word. It's very intensive, very annoying, very boring, but it is, I need to ensure the best quality possible. Also, some locations I'm looking at, I was even looking in locations where radar seems to be looking in accordance with the melt pond locations to make sure from the beginning they have quality, but that is a major issue.
Yes, thanks. It was very interesting, but I can imagine it's very challenging also. And actually, I had some similar question, but also, I mean, the melt ponds are also changing through the summer, so they're changing in shape, and then, like as you say, the roughness change. I guess this is also makes also like it even more difficult. And then one question, which is maybe unrelated to the other one, is have you compared it to other melt pond fraction products like from Olshi or Meris?
Not yet. There are two. One is based, yes, on Olshi from Sentinel-3, and the other is from Modis. This is on a later stage, because another idea that I have is run this on this, because these are way higher resolution, because if I'm not mistaken, those are 500 meters resolution. So on the second stage, I would like to do this, but using those melt ponds. Also, another issue that I'm facing is that I need to ensure that radar and optical data are from the same, as close as possible time acquisition. So I'm comparing images where they are really, first I filter. I want images only 6 hours apart from each other, but sometimes even 3 hours apart, the ice poop already did like this. So I see melt pond here, and on radar, clearly it is already here, and I can no longer use this. It's painful.
Thank you very much.
Thank you very much.
Next, I would like to welcome Jakob Gran, who is going to give a presentation on remote sensing for avalanche prediction towards a digital twin of the snowpack. Welcome, Jakob.
Thank you. So I also work at Norse. I'm located here in Tromsø. I'm specialized in satellite remote sensing. I will talk about how we use this for avalanche detection and prediction. And I will end with some comments on how this relates to digital twin or that concept. So first, this is one example of an avalanche that happened last year, north of Tromsø on Reinøya. So I want to show this firstly to demonstrate the kind of destructive power of the avalanche. In this case, it was naturally triggered, and it swept out a whole farm into the fjord, killing 2 people and over 100 animals. So this illustrates also the importance to be able to predict avalanche danger, to be able to evacuate people. So it's not only something that is relevant to skiers or tourists. Secondly, this avalanche happened at a slope where there hasn't been an avalanche before, as far as we know, in recent history. And that was due to a bit unusual storm that was happening before this, with unusual wind patterns and unusual situations. And with the changing climate, this also opens questions to where will avalanches happen in the future. So it all boils down somehow to, if you want to predict avalanche danger, you need to say something about the stability of the snowpack. That's basically what it boils down to. And for this, you need to basically look at the snow grains, layering, and dig down in the snow to assess the stability. Now, the problem with this is that Norway is big, there is many mountains, and it's really expensive and hard to have people out making these snow pits on very large scales. So this illustrates the forecasting region for we are in now in Tromsø. It's about 100 kilometers in size. So it's really hard to sample this manually. Now, so typically what you do then is that you move upwards and you use remote sensing. The problem is then that you gain coverage, but you lose level of detail. So you cannot, with current sensors, really say something about these detailed, like really small snow grains that you need to know something about from a satellite. That is not possible today. So what can we do then? Well, what we can do is to look at the input, basically to the snowpack. The snowpack is a consequence of weather, of winds and precipitation. And then we can also look at the output, the avalanche events. And these two we can monitor by satellites. So the monitoring of weather is kind of that's been around for a long time. You use radiometers, scattermeters, optical sensors, and you use models to make forecasts of the weather. So I will not talk about that, but I will talk about what we do on the other side of the output. So we detect avalanches. And for this, we also use radar, synthetic aperture radar. So basically what we do is that we look for changes in radar images. And typically what happens is when you have an avalanche, you get a rougher surface and you get an increase in backscatter. So these increases we can see here illustrated as green color in this image. And this is the avalanche that happened last year on Reinøya that we can see. And to be able to handle the amount of data that the satellites are producing, we also then use deep learning. And we've tested a lot of different models, both CNNs, transformers. Typically we see that CNNs perform slightly better than transformers, but the specific details of the architecture doesn't seem to matter that much as the data set matters. And I agree with my previous speaker that it's quite boring to produce these training data sets. So to help us, we've also developed tools to dedicated for this specific task of outlining avalanches, where you can pull in field observations and maps and stuff like this to be able to say what is avalanche in these SAR images. In the next slides, I will show results that are from a feature pyramid network, which is slightly similar to the UNet that was covered before. And also we have put quite a lot of effort into making software just to handle the satellite data, to distribute processing. So we want to do this on nation scales, to be able to deploy it on clusters, and also we do develop tools to visualize this in 3D, as I will show shortly. So this is one example of detections we made for one winter season. This is 2000 to 2001 over Tromsø, or Troms area. And in this winter season, we detected about 7,000 avalanches. And to the left here, you see the distribution of them. And to the right, you see the level of detail we also have. So we have a 10-meter resolution on this data. So we can really, in detail, examine proximity to roads, for instance. So this illustrates the main road leading into Tromsø, the E8. And this also shows how we can visualize them in our 3D visualization tools. This particular road is really prone to avalanches. So this was a few years ago when a car with a guy in it got totally covered by an avalanche. Yes, so we can basically say something about the input and output through satellite data of the snowpack. So what we want to do now, and what is kind of the current activity of what we do, is to link these two and try to make predictions about future. Given a weather forecast, what will the avalanche activity be? So these plots show time series of avalanche counts in gray and weather parameters in this orange. So you see on the top plot here, for instance, you have precipitation going downwards, avalanche count going upwards, and you see clearly that there is a correlation, of course. Yes, so the idea is to build statistical models or machine learning models that is linking the weather to avalanche activity. So in a sense, we are doing the job of kind of estimating stability of the snowpack. So in a sense, you might say, okay, we're doing some sort of model of the snowpack, maybe a digital twin of the snowpack. So this also opens the question, what is a digital twin? I think you get different answers who you ask. But I tried to end this presentation by putting some words into what this might be. You need some visualization, you need data, you need some model. In our case, we're working with machine learning models, statistical models. But we also have plans of integrating physical models of the snowpack. So you might have some physics in there. Yeah, so this kind of illustrates which pieces of this kind of digital twin idea we have currently. Yeah, that's it. Thank you.
Thank you very much, Jakob. Any questions for Jakob? Yes, 2 questions. We can start here with Rune and then over.
Yeah, you showed the correlation with the precipitation, which is not very surprising. But have you looked at the wind directions and how that affects probability in different areas?
Have looked a bit into it. It's not very clear, that correlation, but it's something we're working on. Yeah.
Traditionally, avalanches often occur in slopes that are 35 degrees or higher. Did you look at the slope angle of the avalanches that you found?
Yes, so when we do detection, we also use topography as input to the network. So it's taking these SAR images in addition to actually like slope angle. So this is one important piece of it.
Well, to start the presentation, you said that it occurred where it normally doesn't occur. So I'm wondering if the angle of the slopes is different. Are you identifying that there's new avalanches occurring on lesser angle slopes?
I haven't made any analysis of how they relate to slope, but typically if it's not above 30, you don't have. So in the case, in the Reinøya example, the topography was avalanche. It was avalanche topography, but you also need a snowpack there that is unstable. So, yeah.
Has this been developed in specifically around the regional context of Tromsø?
We're doing it all over all Norway.
All of Norway.
Also, we're working now also in the Alps a bit.
Okay, so there is a transferability associated with the machine learning aspect, the modeling aspect.
Yes. Yeah.
Great. Any other questions before we move on? Oh, one more.
Does it work? You said that wind doesn't correlate.
It's not
that
as...
precipitation seemed to be pretty straightforward, but you said wind didn't. But I mean, we are taught that in Lee slopes don't go there. So how does that fit together with your non-correlation? Is it because it's too complicated, or is it?
The correlation isn't as obvious. So I mean, you can often have wind, but you don't have snowdrift. So you need snow that is loose enough to be able to move, for instance. So the coupling is not as clear as with precipitation. But surely there is a link, yeah.
I guess it's also the temporal dimension. It's the winds from maybe a week ago or a month ago that a tree or created the snow cover that finally released.
Yeah, so this is a big challenge. Is that you have such a long? You probably need to look at quite a long time frame of the weather history to be able to say something. Okay, then the avalanche is triggered. Yeah.
I have so many questions spinning in my head now, but I will save them for one.
Okay, sure.
Thank you very much, Jakob. I think for the last presentation we have Margareta Johansson, and I believe we will switch to a digital format. Margareta will give a presentation on improving access to environmental data in the Arctic with the help of AI. So I think maybe zooming out a little bit. Margareta, can you hear me?
I can indeed hear you.
Great, and we can hear you.
In best case scenario, you can sort of see my screen.
Yep, and we see it perfect.
In presentation mode?
Yep, you're great.
Fantastic. So thank you ever so much. And first of all, I apologize to everyone for not being there. I was up in Kiruna in northern Sweden, and I didn't manage to get from Kiruna to Tromsø due to the weather. So yeah, sometimes it doesn't help to be close by. But anyhow, so I would like to talk about improving access to environmental data in the Arctic with the help of AI. I am not the person who has done this. I am the coordinator of Interact, which is an EU project. But the brains behind this are Carl, Maria, and Thomas, and they're all based at AFRY, which is a European leader in engineering, design, and advisory services with a global reach. So it's a big company that it's worldwide that we have engaged to help us do this. As I said, Interact. So Interact, I hope most of you have heard about it, but just to be on the safe side, it's a network of terrestrial research stations. We used to be more than 90 research stations in all Arctic countries, but since February, no, actually a little bit later, but since the invasion of Ukraine, we are currently pausing the collaboration with our 21 Russian research stations. But as you can see, we had an Arctic-wide coverage before that, and we hope that we will get back to that as soon as the war ends. Interact, as I said, it's a network, but it is an EU infrastructure project. And those EU infrastructure projects, they always contain three different things. So the first thing is networking. This is where the station managers learn from each other and develop a lot of best practices, how to run a research station, how can we improve them, how can we ensure that what we are monitoring is actually in a way that it can be used, etc. Another part of an infrastructure project is to actually provide access to the research station, both physical access in terms of funding scientists to go to the field to do field work. And then also there is something called remote access, which is having scientists to tell their research station staff what to do. This is, of course, more environmental friendly, but not suitable to all research projects. And then also virtual access, which is the data portal with metadata that where you can, which is linked to real data, and you can access real data from quite many stations there. In addition to that, we also have something called joint research activities. These are different aspects. So we decided that we wanted 6 different joint research activities for Interact 3. And they were societal challenges that we thought were sort of important for the coming 5 years when we started this in 2020. So it was about extreme weather events, about transport communication, about making data widely available, about improving education and awareness at all societal levels, about documenting and reducing pollution, and then the last one is about the impact of increasing Arctic tourism. But as you can see, I put one in bold, and that is what we are going to focus on here. And that is making data widely available. As I said, we are a network of, now we are 75 research stations, but more than 90 a couple of years ago. And some of the research stations in Interact, they have been active for more than 100 years. And of course, more than 100 years ago, we did not have computers. So you can imagine that we have hidden data. There can be sort of a little gold mine there. This is just one example where you can see the Arctic station in Greenland, which is the oldest one, which was actually established in 1906. So the whole idea was to try to discover some examples of these old resources in text and or image format, and then use AI and machine learning to rescue data on environmental change, try to increase the awareness among station managers of AI and machine learning and what they can achieve and the prerequisites for using them, and then also produce a best practice scheme for the use of this methodology at Arctic research stations. We started, of course, in 2000, not of course, but we started in 2020. And the first thing we did was to try to figure out how these station managers, are they aware of AI and ML? I mean, if we would do the same survey today, then of course the answers would look completely different. But this is what we started off by. So most of the station managers, they did not use AI, and there were a few that were sort of planning on using it, and there were quite many that thought maybe, and then there were a few that said no. And then also they tried to identify what type of data accessible they had from their respective stations that could possibly, where we could use AI and ML to improve the work. So many of the station managers knew very little about AI and ML. So the first thing, AFRY, I must say, I really recommend working with these companies. They are brilliant and they are professional, and they can really explain things in a way that actually, I would argue, most people can understand, which is lovely for me, who doesn't know a thing about AI and ML. But they started to have workshops to bring us up to speed, sort of the background of AI and its concept. And of course, this was just one example during Corona where they could see immediate how we could use it, and then to determine some hazards, telling us about computer vision, and how to train it, and optical character recognition and natural language processing, and some of the machine learning services that you can learn about. And then the next step was sort of try to find what hidden treasures were available at the different research stations. Were there any examples that we could dig into and then sort of try to do something about and develop a concept? And I'm just bringing up two examples here. And the first one is from the Tafala Research Station, which is located not very far from where you are seated at today, but it's in the north, close to Kebnekaise in the Swedish mountains. And that station has been running since 1946, and they have a lot of logbooks with diaries with information that could be extracted. So then sort of that was the starting point. We have logbooks. How can we actually get something out of these logbooks? So they were working on automated digitization and summarization, and then of course comparing the AI and the human summaries. As I said, they were using handwritten notes and books, and it takes a lot of time to type them. So how to save time for researchers. And in the end, the results indicated that performance from the AI using optical character recognitions and natural language processing to that could be comparable to what humans actually did. So that was very time saving, of course. And then another example of data that were available. This is from the Cairngorms research area in northern Scotland, where they have had quite many years an automatic camera taking photos. And then how could you classify these images? It is very time consuming doing it on your own, but they actually trained the system and concluded that it actually worked very well. Also, not just identify the images, but being able to identify different animal species. And then, as I said, they wanted to develop some future strategies for AI and ML to use at the research stations in the Arctic. And the first thing they sort of concluded was scientists rely on open source tools, packages, models, and programming languages. And the best thing is to use the ready-made commercial solutions. And prerequisites to using machine learning is the knowledge on how to handle the data sets. And then they listed an example or some examples of methodology. So, for example, one way to do it could be to list resource consuming and manual tasks at the research station. And when you have identified the source, then you should consult a data scientist or a machine learning engineer experts, which we have done through AFRY then, but there are others, of course, we can hear from the room today that you can consult. And then we have worked very successfully by including master thesis students from IT or data engineering science who actually have a little bit of time to put into this. So also keeping the cost down. And then the students presenting their work with a focus on learning outcomes and future development, but of course being supervised by the experts. And then the last step would be to evaluate what went well and what can be improved and whether the proof of concept can assist in Arctic research. More information about this can be found on our website. There is a little part which is called AI. So under that, if you click that button, then you can find more specific information and more details about all the methodology that has been used that I have. Where I am very happy to say, as they do in Fawlty Towers, I know nothing. I'm from Barcelona. And by saying that, I hope I didn't offend anyone in the audience. And then, of course, we have Facebook, X now, not Twitter, it's X now, and then Insta. So please join us. Thank you.
Thank you very much, Margrethe. Any questions for Margrethe before we have a pause? Short pause. I wish you could be here in person to join us for the full session, but thank you very much for joining us online, Margrethe.
Thank you very much for providing the opportunity.
So far we've heard about innovative data solutions and innovative modeling solutions for some specific opportunities to integrate machine learning and AI towards some sort of notion of a digital twin. And after a short break, half an hour, I hope that you will join us again as we continue the conversation and transition the topic and broaden the topic perhaps more towards the applications and the possibilities for applications of this new and exciting path of our work. So I believe there's some refreshments outside, and I hope you join us for the second session and, of course, the panel session that will follow our presenters. So thanks for joining us.